Welcome to the last talk before the lunch break. It's going to be Ying and David Lawrence, Introduction to Threat Modeling. Give them a hand.
Right, yes. Welcome to our talk, Introduction to Threat Modeling. I'm David.
And I'm Ying.
And we both work on the Docker security team, where I mostly work on all of our signing projects.
I mostly work on Swarm Secrets and PKI.
And as a part of our day jobs, threat modeling is one of the things that we have to do for the various components within Docker, and even the components composed into larger systems, to make sure that we're not introducing new vulnerabilities to the people that deploy their applications onto Docker. And I have to apologize up front that we're going to throw a lot of information at you in this talk. There is a certain base process that we have to get through to give you a useful threat modeling system that you can take away and use. If anything just doesn't stick, the talk is obviously recorded and you'll be able to refer back to it later. So what's threat modeling all about? Well, a lot of software as it grows gains features organically. There's code churn. People think something is a good idea and then rip it out maybe not as cleanly as they should. So you end up with this sort of bizarre system where the code might do an amazing array of things and it does everything you need it to, but the security posture of it hasn't been very well considered. And threat modeling is going to help you take your security posture from that bizarre model to a cathedral. At least you can have a bazaar inside this cathedral. There's a fantastic old church back where I grew up that has a climbing center inside. It's kind of crazy. But on the outside, at least, your security posture needs to be well-designed, well-thought-out, well-architected. Because otherwise, you're going to spend the rest of your career maintaining software where you're playing whack-a-mole and constantly trying to chase down vulnerabilities after the fact. And what does this result in? Well, we saw that earlier this week. This is a total failure of an IT operations team to appropriately threat model the systems they're managing. They didn't consider updates to be important enough, so they let them slide. And to aid us in doing an actual threat model, we're going to use two systems to show you how a threat model can be applied over both real-world examples. In this case, we're going to model our imaginary house, but also abstract software examples where most of us really need it. And we're going to use a very simple Django photo gallery type application that we've built. There's going to be no code, conceptualize some kind of simple photo gallery built on Django. And note, you can and should apply threat modeling at many levels within your system. The components themselves should have been threat modeled by somebody. On my house, I have locks. These should have been threat modeled by the lock manufacturer. They should have thought about the way that somebody is going to try and break that lock, whether it's lock picking or bump keys or just drilling it out. They should be using appropriate security measures to beat those vulnerabilities. For my Django application, I use the cryptography library. The cryptography library has been threat modeled by various developers to ensure that the interfaces it exposes for you to use, the approved methods of using it, are safe to use. You can also step up. You can threat model the platform that you're building on top of. For our house, this is the city. Hopefully, the city council has gone and modeled things like the emergency service access to various parts of the city. They've made sure that there's a fire hydrant within a certain distance of any property. For our application, this is going to be the infrastructure we're deploying on top of, which may incorporate AWS configurations, our CI/CD pipeline, something like a Docker registry where I store my built artifacts from my CI/CD system. And we need to look at all of these pieces individually and threat model each of them so that we can make sure our entire end-to-end system is secure. But we can threat model them as these pieces, right? We threat model our application. We can deploy many applications into the infrastructure, so we can threat model the infrastructure separately. Similarly, we might use our cryptography component in many applications, so we're going to threat model that as an individual component. And it's up to you to kind of find what these logical pieces are within your systems, within your applications, within your infrastructure, to make sure you're threat modeling things appropriately. Now, threat modeling itself involves a process. It's important to have a process because you want to be able to apply it reliably over every single component that you need to threat model. You're going to end up with a list of vulnerabilities and remediations and a prioritization of how you're going to fix them and in what order. You need to be able to prioritize all of your vulnerabilities across your organization to make sure you're fixing the worst vulnerabilities first. And this process consists of 3 steps. The first step is collecting data. We have to know what we're actually doing before we can start making decisions about it. So we're going to look at what types of information, what categories of information we need to collect about our application. Next up, we're going to analyze that data. And we have a structured methodology for analyzing the data we've collected, combined with our kind of intuitive knowledge of how our systems work, to come up with vulnerabilities that we find within the system. And finally, remediation. For every category of vulnerability, there is a set security control that can be used to mitigate that particular vulnerability. And the implementation details are going to depend on exactly your system and what you're trying to fix. Obviously, the way you mitigate an information disclosure problem in a house versus in a software application are going to be completely different. But there is one class of security control that gives you a particular type of implementation solution to look at. So up first, collecting data. Now we're going to look at what the categories of data are first, and then we're going to look at some specific examples of what this data would be for our house and for our Django application. So the first piece of data we need to collect is our list of external dependencies. These are essentially things that we're going to rely on somebody else to have implemented, designed, and threat modeled appropriately. These are going to be infrastructure we deploy onto or components that we pick. And we're going to make decisions about which of them is best, but we're not going to go and dig into the internals and threat model them themselves, at least not as part of our application house threat model. And it's important to do this so that we can laser focus on the rest of the data that we really care about. So up next is entry points. This is how data gets into our system and comes out of our system. An entirely closed system is generally very secure because you can't actually interact with it in any way. We have to have some kind of mechanism for interacting with our system, and this is where vulnerabilities often originate. So we will enumerate all of these as part of our data collection. Next up are assets, things we care about protecting. This might not necessarily be everything, but they're things that have value. And they can be both physical assets, which are relatively straightforward, things somebody can pick up and carry away with them, but they can also be consumable assets. Not every attack is coming after our data. Fourth up are trust levels. These are the tiers of access within our system. Who do we expect to be doing what, and what are the controls in place? And we need to tie our trust levels back to our assets and entry points to make sure that people with a given tier of access can only use the entry points that we expect them to use and can only access the assets we expect them to have access to. And finally, we have data flows. Data flows are diagrams that describe how information moves around our system. And most importantly, they describe what we call trust boundaries. And we're going to look at what these terms mean in more detail later. But trust boundaries are essentially where data is elevated in privilege.
So now that we've described the different types of data, let's go over some examples. So first up is external dependencies. One type is third-party services. So for example, for our house, we might contract an external security company to maintain our security system, or an HVAC maintenance system company to maintain our vents and AC. For our application, we of course trust in PyPI and Python core to have appropriately threat modeled their application and to maintain features and security guarantees. But we also might trust third-party monitoring services such as Prometheus, certificate authorities such as Let's Encrypt, or CDN and caching services such as Cloudflare. We depend on the city where our house is located in order to provide us services, to make sure that our water and sewer is guaranteed to our house, for instance. This is similar to our application where we depend on our chosen deployment platform. We've probably vetted the platform to make sure that it has the features and security guarantees that we need, but we don't actually know anything about how it's maintained internally necessarily. We depend on the platform providers to do that. Similarly, we depend on the in city departments such as the fire department or the public works department to make sure that the connection to our house, the water and sewer and electrical connections, are maintained and operational. For our application, we rely on our ops team to correctly set up our host configuration to provide the security guarantees that we need, to restrict root access to our host systems, to make sure our IAM roles are set up correctly, or to make sure that the swarm secrets that we need are already present on our production system. Even if we are our own ops team, we will be threat modeling the host configuration separately because, as David said, we want to laser focus on our application. And also, if you threat model multiple systems simultaneously, the complexity of your model increases combinatorially. And finally, we rely on our car manufacturer to secure a car, to make sure that it's relatively unpickable, to make sure that the alarm system works. And we evaluate all this before we decide whether or not we want to place our garage door opener, which gives anyone access into our garage, inside the car. Similarly, we can guarantee or we can require that our clients use modern web browsers. We can enforce that they only use versions that support, that correctly implement HTTP-only cookies, for example, or support HTTP secure flags on cookies. Next, we need to enumerate the entry points to our system. So there are two types. We need to identify the intended entry points, which is where we want users to interact with our system. For our house, we want our visitors to come in through the garage or the front door. For our Django app, which is an HTTP application, we want users to come in through the open HTTP port through our WSGI server. But we also want to make sure we enumerate any unintentional entry points. So for our house, windows provide light and ventilation. But if they're improperly configured, someone could also climb through the window and use it to enter our house. For our Django application, we expect that the SQL server is only accessed by the Django application. However, if the SQL server itself is incorrectly configured, or we have some vulnerability in our Django application, then someone might be able to access the SQL server directly, completely bypassing the Django application. Similarly with the file storage and thumbnailer service. Next, we want to enumerate all the assets of our system. These are the parts of your system that are valuable both to you and to an attacker. So for our house, this is our passports, our valuables like our actual money or gold, sentimental items such as photos, electronic data, and of course, consumable utilities such as electricity. We don't want to be footing the electric bill for a neighbor. So for our Django application, we have physical assets that people can take away, such as our TLS user and API credentials, user-generated content, photos, blog posts, comments, as well as consumable CPU and bandwidth. So one example is, for instance, the Mossack Fonseca breach last year, where there was a vulnerable WordPress plugin that allowed someone to upload arbitrary PHP code. They use that to exfiltrate the physical data, but they could just have easily used it to mine Bitcoin, using up compute resources, or used it to attach the host to a botnet to attack other servers, using up both bandwidth and compute resources. Notice that we did not say your assets include everything on your system, because there are probably items on your system you don't particularly care about. For our house, for example, we don't really care if someone steals a couple rolls of toilet paper, unless it's the last roll. For our application, we don't really care if people delete the PYC files. They're temporary and are regenerated anyway. The only reason that the theft would matter to us is that it indicate that someone had access to our more valuable assets, the stuff we actually cared about. Next, we want to enumerate all the intended trust levels of our application and of our house. So for our house, the most trusted and highest privilege level is residents, us. We have the keys, we can change the locks, we can change the security codes. This corresponds to the Django admins for our application. They can create users, they can remove and add features, delete databases. The next level for our house is a guest. They might be an overnight guest who's allowed upstairs to the more private second floor. have access to the guest rooms, bathrooms. This corresponds to a moderator in our Django application. This is someone who has access to ban users, can delete posts that other users create. Even lower on our house access list are temporary visitors. This might be a local Girl Scout whom we'd gladly invite into our foyer so we can buy lots and lots of cookies. For our Django application, this could be a registered user who is allowed to make posts and read other public posts from other users. Finally, the lowest level, the base level of trust, is a passersby on the street who's not even allowed into our house. This corresponds to an anonymous user to our application. Now, we may not allow anonymous users to do anything. They may just get a 404 page or a login page when they visit our site. But any threat model needs to include this base trust level as part of the data collection step, because this base trust level is the level used by an untrusted attacker when they're trying to gain access to your system. Finally, we need to diagram our data flows. Not a list this time, just a diagram. So data flows are represented with 6 types of symbols. There's a circle for a single process that handles data, double circle for multiple processes. These could be multiple replicas of our service, or possibly multiple different processes that represent a single logical unit that will be diagrammed in a separate diagram, just because too many components can't fit on a single diagram. Rectangle represents external dependencies, which we've already covered. A double line represents a data store, and this could be like a file system, cache, or database. An arrow represents a data flow, which is the direction in which data travels through your system. And finally, a red dotted line represents a trust boundary. Trust boundary is a change in trust levels as data moves through your application. Data that passes a trust boundary has to be analyzed carefully, whereas data that flows within the same trust level in our application is scrutinized much less. That's why entry points into any system must cross a trust boundary. So any threat model and any data diagram, as data flows through an entry point, it must cross a trust boundary, because that's how untrusted data might be accepted into our system. So now that we've gone over all the symbols, here's a basic data flow diagram for both our house and our application. We've modeled this so that they have sort of a hard shell, soft interior model, because we've added trust boundaries to the entry points as is required. This means that we only care about the perimeter. The entry points are the only points at which data is authenticated, authorized, or validated. Once inside the system, like once inside the garage, someone can move directly into the house or have access to anything in the garage. And all the components of our application, except for the Django application, just trust whatever data or connections are handed to it, because they're assuming that it's coming from the Django application itself. This is not a good model for security. And next, we're going to go over how and why, rather than just securing the entry points, we should be securing all the individual components instead.
Okay, so we've collected all of our data. Now we need to actually do some kind of analysis of it to determine what the vulnerabilities are within our system. And we use a 6-step process. They're not really steps, they're parallel lines of thought. Stride is a vulnerability classification system, and it's one of many, but we found it works very well because it helps you think about certain types of vulnerability. Each of these letters stands for one category of vulnerability that you can think about in turn with the data you've collected to work out if there is some way of exploiting your system. So we'll go through each of these quickly with some examples. We'll then prioritize all of our vulnerabilities, and then we'll talk about how we're going to remediate them in the final step. So up first, S is for spoofing. Spoofing is an entity pretending to be something that it's not. For example, somebody knocks on the door to your house. They're a plumber, but you didn't know this until you opened the door for a start. Additionally, you don't necessarily know how or what credentials you should be looking at to confirm they're a legitimate plumber that you should let in, and not just somebody your landlord, or not somebody who's claiming your landlord sent them around, but they really just want to steal your valuables. This is kind of similar to a brute force attack against our Django application. somebody we don't really know, but we're going to give them the login page, and they're going to knock on the door really hard over and over again in the hope that we're going to let them in. And our Django app isn't especially well designed at this point, so it's just going to let them keep knocking. Next up, T is for tampering. Tampering is violating the integrity of data in some way. Maybe one of your housemates is a smoker and he doesn't like going outside in the rain. So he puts a bag over the smoke alarm or otherwise disables it in his room. This is bad. Similarly, somebody could use a SQL injection against our Django application to disrupt our database in some way. There are a lot of things you can do with a SQL injection. We're going to see it appear against actually quite a number of these vulnerability categories. But somebody in this case could use a SQL injection to change data, remove data, maybe users end up getting displayed something they really don't want to see. R is for repudiation. Repudiation means the ability to say after the fact, I didn't do it. So in the case of our house, maybe a kid throws a stone through the window. We know they did it, like we saw them throw the stone, but we have no proof of it. We're simply pointing a finger and it's our word against theirs. What we really want is some way to confirm that this kid really did throw the stone through the window. Similarly, if we have a malicious admin within our system, we probably want to be able to prove that he actually carried out certain malicious actions. But unfortunately, our server isn't very well configured, and he can just go and remove the logs because he's an admin. And now we have no trace of the fact that he, say, created a malicious user account that he's been using as some kind of backdoor. We're starting off with the bad version, okay? I is for information disclosure. Now, in our house, this is obvious. We have a slightly Spartan house, so you can just see in through the windows. For our application, we have really bad messaging on the login form. When you put in a bad username, it tells you it's a bad username. So you can, through a brute force enumeration, you can discover maybe not an exhaustive list, but certainly a lot of common usernames that may exist within our application. D is for denial of service. Somebody preventing you getting access to the resources that you're trying to protect. In the case of our house, some neighborhood kid came around and thought it would be funny to glue the locks shut, and now I'm locked out. In the case of our application, we have the classic distributed denial of service. Somebody is just flooding my server with so much data that legitimate users cannot get an answer. And E, finally, is elevation of privilege. Now again, our house is relatively old, and the people who originally built it lived in a much more trusting time, so they didn't put a lock between the garage and the house, which means if I accidentally leave the garage open, somebody can get full access to the rest of my house and steal all of my things. In our application, again, a SQL injection is a relatively straightforward way for, say, a registered user who has a record in your database to just change the flag that says what type of user they are and elevate themselves to an admin, allowing them to perform any operation they want within the system. And having come up with a set of vulnerabilities, we need to prioritize them. And we'll take two specific vulnerabilities to help us in this prioritization. Let's take our information disclosure. Somebody can see in the windows of our house versus our elevation of privilege. Somebody can go from our garage into our house without any further authentication. And there's a simple two-metric system we can use to relatively prioritize all of the vulnerabilities. First is impact. How bad is this vulnerability going to be if somebody makes use of it? Let's assume they found it. How much damage can they do? Now, for the case of our information disclosure, if it's just people can see who's inside the house, this may not be a big deal if I'm not trying to run some kind of secret society. But for our elevation of privilege, the impact is pretty extreme. If somebody is able to make use of that vulnerability, they've just stolen all of my valuables. The second metric is probability. How likely is it that somebody can actually find and make use of a vulnerability? For our information disclosure, the probability is incredibly high. Anybody walking by the house is able to see that there's no curtains in the windows and is able to make use of this vulnerability. Now, for our elevation of privilege, the probability is much lower because, for one, you kind of have to know that the lock doesn't exist between the garage and the house, and my garage door is generally closed. You may also have to compromise my car to get my garage door opener, to open the garage door to get into the house, and we've already established from our external dependencies that we rely on buying a car that has a good security system. I also typically park my car in the garage, which adds another layer of defense. And when we balance these two things, we typically add them together. You can average them if you want, but the ordering ends up the same, and we get a score for each of our vulnerabilities. Now, you may want to categorize impact higher than probability, because even if the probability of our elevation of privilege is low, the damage is so high, should it be exploited, that you may want to look at fixing these higher impact things first. So we can always weight this system by doing something like double impact plus probability to put the higher impact things first. But impact versus probability is kind of a maybe overly abstract way of scoring things. People can disagree on how bad something is, how likely it is to happen. So often we use a scoring system called DREAD. DREAD stands for damage potential. This is how much financial and reputation damage will exploiting a vulnerability do to both you as an organization or an individual and your users. R is reproducibility. This is how likely is somebody to be able to use this vulnerability over and over again. Note that if there's some kind of timing aspect, you may not actually be able to use the vulnerability with 100% reproducibility. E is for exploitability. This is a measure of how much resource is required to make use of the vulnerability. If it's something that somebody could accidentally stumble across in their browser while they're just navigating your website, the exploitability is going to be incredibly high. If, on the other hand, it's something that requires nation states to actually compromise, the exploitability is incredibly low. And often people will use this measure when they talk about actors and how, like, you know, our system isn't meant to protect against nation states. Well, a much better way of doing that is to use something like DREAD scoring and say, you know what, we don't care if the exploitability is a score of 1 out of 10, because 1 represents nation states. It's a much more objective way of deciding what you're going to exclude. A is for affected users. This is how broad is the scope of the vulnerability. If it only affects, say, completely anonymous, unregistered users, and your website is an entirely private thing, maybe it's not so bad, but it may be something you want to look at. If, on the other hand, it is something like a SQL injection that can manipulate the database, this is going to affect everyone in your system, and you want to fix it as quickly as possible. And the final D is for discoverability. This is how likely somebody is to find out the vulnerability exists. Again, high discoverability would be somebody stumbles across it using, say, Scrapey, just going through all of the URLs in your website. On the other hand, if it requires intimate knowledge of the internals of your application, the discoverability would be considered very low. And now each of these is often scored on, say, a 0 to 10 point system, but as long as you're consistent, you can use any scoring system you want. So you could use 1 to 3 to just do a simple low, medium, high type system. We then add all the numbers together, and again, it gives us a prioritization of all of our vulnerabilities. And note, if we need to give a summary of this to somebody else, we can compose these back into our impact versus probability metrics, where damage potential and affected users corresponds to impact, and reproducibility, exploitability, and discoverability corresponds to a probability that somebody will find and use a given vulnerability.
So now that we've gone through Stride, we can decide on and document how to remediate the vulnerabilities. For each letter in the acronym Stride, there's a general class of security control used to remediate that type of vulnerability. It doesn't mean that you're restricted to only that type of security control, much like how SQL injection can be classified as both tampering, information disclosure, denial of service, and elevation of privilege. You can combine multiple classes of security control to remediate one type of vulnerability. But I'm just going to give you the general class, one-to-one matching for security control type of vulnerability. So we're going to go over both the control and the specific implementations of that control to remediate the vulnerabilities we discussed in our analyzing step. So for spoofing, the general control is authentication. For our house, when a plumber visits our house, we hope that we have a peephole in the door or a window so that we can make sure that the plumber is the general plumber for a housing association. Even better is if the housing association sends us a notice letting us know to expect a plumber to visit us on such and such date at such and such time. Similarly, for our Django application, we want to have strong user authentication, maybe using two-factor authentication, but we also want to authenticate the login request. We want to make sure that it came in, the form was submitted from our site and is not a cross-site request forgery. The general control used to mitigate tampering attacks is integrity controls. For our house, if someone tampers with our smoke alarm, we should validate on a regular basis that the smoke alarms are in good working order and have adequate battery life. For our Django application, we want to validate input whenever a user hands us input. And we want to validate the checksums of the data both at rest and in transit to make sure it hasn't been tampered with. For repudiation, unfortunately, the control is unhelpfully named non-repudiation. It's not very descriptive. But this basically means implementing audit trails. For our house, we're going to install a security camera, so if a vandal comes by and knocks out a window, we have evidence to indicate which vandal broke our window. For our Django server, we can implement append-only logs that are impossible for even administrators to delete. We could replicate the logs to multiple servers that the admins might not have access to. We might require that every single operation, including log manipulation, requires digital signatures so that an admin cannot possibly repudiate an action that they've taken. Information disclosure is controlled by confidentiality. So for a house, we can just install curtains. If we really don't want any information leakage, we can install blinds so that no one walking by can tell if anyone's in the house. For our application, we encrypt data at rest and also in transit using TLS. We can redact sensitive data when it needs to be displayed. For instance, if a user needs to look at their settings and change their password, we don't display the password. We make sure that our configuration is set up so that logs, for example, don't print out passwords. And then finally, or not finally, second to finally, for denial of service attacks, the solution and control is providing better availability. So for our door lock that's been glued shut, if we had a digital lock, then we would have two methods of entering the house, both using the key or a digital code. For our application, we could be running more replicas of our Django server, and we could also have robust recovery protocols. For instance, if a user accidentally locks themselves out of their account, then they've denied our service to themselves. If we had a robust recovery protocol in place, they could recover the account without our interference. The final class of vulnerability and control is elevation of privilege that can be mitigated via better authorization. And authorization is different than authentication in that authentication says who you are, authorization says what you can do. So for our house, and they're pretty much tied together. So for our house, one way of having better authorization is just to include another door between the garage and the house so no one can move from the garage to the house without having to re-authenticate themselves. For our Django application, we need a well-defined auth model utilizing the trust levels that we enumerated before. Each operation should require the least privilege necessary to perform that operation. So a user that, an administrator, for instance, who is just navigating around the site can navigate around with the privilege of a regular user. And when they need to perform admin functions, they should re-authenticate. And as they're re-authenticating, we authorize that they are allowed to perform the admin function that they want to do. So with all these remediations in mind and possible vulnerabilities that we've discovered previously, we redraw our data flow diagram. We've included trust boundaries now between every component. So if someone enters our garage, they will need to further authenticate by having a key to enter our house. We might want to keep our tools in a toolbox that are locked so that if you have access to the garage, you can't steal whatever is in the garage. Similarly, if someone has access to our house, we may not necessarily want them to have access to all our valuables, which we store in a safe. For our Django application, we make sure that all the P components communicate with each other over mutual TLS. We may want to do additional data verification when an image is submitted from the Django site to the thumbnailer to make sure that the thumbnailer is not vulnerable to like image magic vulnerabilities. Okay, so so now that you know how to threat model a single application, we can talk about how to integrate this process into your development and deployment lifecycles. So this is a threat model for your current application, which we've just produced. As you scale up, you want to make sure that new components are added to the threat model, new vulnerabilities are remediated, and old remediations are not invalidated by any new features or any new code that you add. As you change your deployment methods, you want to redo your infrastructure configuration threat model to make sure that things are still set up with the configuration that your application needs. For instance, you want to make sure that all your IAM roles are set up. We're going to make sure that if we're using Swarm on Amazon EC2 instances, that we're using Swarm secrets, that the Docker socket is authenticated, and as this changes, you want to update the infrastructure threat model. Finally, we want to threat model the individual components of our system if we're the ones responsible for developing them. If we're not responsible for developing them and we're relying on third-party libraries, we want to make sure that our usage of these components continues to not break the threat models or security guarantees that the components have. So we don't want to munge with any private fields in any of these libraries, don't access fields with underscores. If we're using cryptography, we want to make sure that we're using the recipe layer and not the hazmat layer, which has no guarantees. If we're using the Django ORM, we want to make sure we're using models and the query functions that are provided by Django. If we, for some reason, need to execute a raw SQL query, then we are now beyond the security guarantees provided by Django. We need to make sure that our usage of the raw execution SQL statement uses parameters and not string formatting. So we might want to add static analysis steps and additional SQL injection detection steps to our CI system to make sure that we are still providing the guarantees that we require in the application.
All right, so in summary, the quick high-level view. We gave you a process of 3 steps. You collect data about your application, you analyze that data, and then you come up with remediations. While you're collecting data, you divide it into 5 categories: external dependencies, entry points to your application, assets you want to protect, the trust levels you expect to be operating within your system, and the data flows, how information moves around. You then use that to think about what vulnerabilities exist in your system using STRIDE: spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. And having come up with a list of vulnerabilities that an attacker could find within your system, you look at the remediations you can use to close off those holes. And you prioritize your vulnerabilities to work out which ones you want to fix first, either using a relatively straightforward impact probability scoring system or using the more verbose dread scoring system. And once you've done all of this, you iterate. You iterate at different levels within your stack, components, applications, and your infrastructure, and you iterate over time because applications change and new vulnerabilities will appear. If you're interested in learning more, the Open Web Application Security Project, OWASP, has some fantastic resources on this. And tomorrow, one of our colleagues is giving a talk on using state machines to secure certain aspects of your systems. Thank you, and I think we have a couple of minutes for questions.
We have about 5 minutes for questions. Please come up to the microphones if you have any.
You did well.
Thank you. Sorry, my throat closed up halfway through.
It's good.
Cool. No questions, because it's lunch.
The best type of talk.
Yes. Awesome. Cool. And we're done.
No questions.
Oh, question.
Oh.
Hi.
Hello.
Hey. We met yesterday.
Should I just start asking? I've never done this before. Okay. I was just curious. You said that, like the external dependencies, you expect them to have done threat modeling. Would it be, do any external dependencies make their own threat models public in any way? And would that be useful at all for folks generating their own, like if I'm generating a threat model for my Django app and I use that cryptography model, I mean, especially since it's open source and everything, say they have their own threat model documented somewhere in their GitHub repo or whatever, would it be useful for me to look at that? Would it be useful to encourage more projects to make their threat models public, or is there danger in that? I was just curious.
Yeah, definitely. A lot of some projects do provide public threat models, not necessarily as formally as this for documentation purposes, because you really have to read through like all the enumerations of lists in order to understand it. It might be more prose, but it would be nice if more projects provided some threat models. I believe Kubernetes has a good one for secrets. Swarm sort of has one. We're working on providing a better one. I'm not sure. I haven't seen that many other open source projects provide one aside from Vault, like things that are very security related. But it would be nice if other projects, even not necessarily very security related, provided some.
Cool.
I'd also add specifically the entry points in a threat model are the expected ways that people interact with the system. So that can actually be useful in determining, like, am I doing something they didn't think of? And therefore, am I exposing myself to a vulnerability that might not be covered?
Okay. Cool. Thanks.
First of all, that was an excellent presentation, very focused and informative. Thank you. My question is, do you do any practices regarding discoverability? And you did kind of mention static analysis there. I'm wondering if there's anything else in that line, discovering vulnerabilities, in addition to the analysis that you were explaining already.
So static analysis is one component of discoverability. But often if we can do static analysis on the code, we have internal knowledge of it. So things that are found via static analysis are, I'm not going to say always low discoverability, but they tend to like shift towards that end of the spectrum. Things like using there's a bunch of external scripting tools that will just like hammer your website to see if it has CSRF vulnerabilities, XSS vulnerabilities. Those kinds of things are the things that have high discoverability. Somebody just looking at the outside of your application can find those things. So I think Ying mentioned running tools like SQL map towards the end. That attempts to discover SQL injections.
I think Burp Suite also looks for the OWASP top 10, so CSRF, XSS, some others, I think.
Yeah.
So
we would definitely recommend adding tools like Burp,
SQL
map, like to your CI system as part of your integration or like systems integration testing to make sure that like essentially the really high discoverability things that if you don't cover them, some like script kiddie is going to send you like, hey, I ran this thing on your site and you have a vulnerability, and then they're going to ask you for like swag and yeah. So definitely run those kinds of tools.
Okay.
it's possible you get false positives, but like so static analysis is better for confirming. But if
Sure.
you don't have access to the code, those are the things to run.
Fuzz testing?
I'm sorry?
Fuzz testing?
Yep.
Yeah, fuzz testing
Yeah.
would be awesome for input validation.
Hi, great talk. Thank you for discussing it. My question is about the DREAD acronym. I liked that because it seems like it gives it a more tangible way of assessing risk, and that's something that I've always found very difficult, is how to assess risk. And so I'm wondering if you guys know of a database or literature source where you could see examples of things that typically go wrong in an application that might be similar to yours, like, and how to better identify how risky something is, because I can kind of sit and think all day of all the things that could go wrong, but I'm probably going to miss some that are important, and so I think it would be useful to see how risky are some of the security flaws in other people's programs, and do you know about any of those kinds of
OWASP has
sources?
a list of top 10 web application security issues. They also refer to a bunch of other lists. So stride and dread is one method of analyzing vulnerabilities. They have a list of several others. I think ASF is one of them, which we didn't choose because it has no nice mnemonic. But it lists a bunch of categories and very common vulnerabilities in those categories that you should always test for that can escalate to like a bunch more vulnerabilities. So,
Okay. So OWASP would be your go-to.
a good place to start at
Yeah,
least.
it's a great starting point for web applications.
Okay.
So sorry, we're out of time. Thanks for all the questions. Thanks for the talk. Let's thank the speakers again.
Thanks.
And now it's lunch break.